Okay everyone, welcome to your first lesson in Flight Dynamics and Control. From now on we will refer to it as FDC for short because it's a really long word and I don't want to write it a lot. Okay, so first of all we're going to be going over what exactly is Flight Dynamics and Control and what is it used for and what will we do, what will we be doing for the rest of the class. Let's see. First of all, we're going to start of what is FDC? Flight Dynamics and Control. It is broken up into two parts. It's broken up in the flight dynamics, and it's also broken up into the control aspect. The first part, flight dynamics, that is the study of motion of the aircraft. It's the equations of motion. Just finish writing this up. So flight dynamics, it's the study of motion. More specifically, the study of motion of the aircraft. And then the second part, the control, that is how we control the aircraft. It's how do you steer the aircraft, the control surfaces, and how that all works into the flight dynamics and how they affect the equations of motion. So it's a little bit about that. Next we're going to move on to I guess we'll skip in different orders than I told you. We're gonna what will we be doing in the class? Well, first of all, we're going to derive the equations of motion, and as we will find out, actually we'll do EOM, that'll be the equations of motion for short. We will derive the equations of motion. These include the torques and the moments. Those are the same thing. Torques, moments, the forces on the aircraft, and then we will solve them. And as it actually turns out, it happens to be 6 differential equations. 6 differential equations. Screwed that one up. 6 differential equations that we need to simultaneously solve. So we'll learn how to solve those as well. Secondly, we'll learn the relationship between the equations of motion and then the aircraft design. And aircraft design. For example, how big the wings are, the control surfaces, where they're located, where the engine's located, how those affect how the airplane flies. Let me just finish this up. Okay, and then thirdly, we'll learn the basics on how to get predictable motion. How to get predictable motion by applying the equations of motion with the control surfaces. Okay, and then that's that part. Okay, next we have what is FDC used for? Well, I'll go over just a few examples of what it's used for. First of all, it's used for aircraft design. It's also used for aircraft operations. And I'll just go in more depth on that in a second. Those are like such as training and aircraft accident investigations. And then finally, aircraft automation. Okay, first we have the aircraft designs. Move that up. What I mean by that is what they actually designed the aircraft for. Like key things they keep in mind is the stability. Not just stability, but more specifically the roll stability. By law, aircraft are required to be able to take off without all their engines. So for a two engine aircraft, they have to be able to take off with just a single aircraft, and they have to be able to account for it. Because if you think about it, if it's a two-wing aircraft and there's two engines on both sides and one of them blows out, you're going to have a huge moment force trying to spin it around. So they have to actually have big enough control surfaces on the back in order to counteract that moment force. So, and for roll stability, for example, there's a couple things that affect the roll stability. There's one, it's the swept wings. So I'll just draw a quick example of what that looks like. Let's see, I think this kind of looks like an airplane. So we have these swept wings back here. That, and we'll go over in more details later on, but that, just trust me for now, that increases the stability, the roll stability, as in how likely it is to bank left or right. The second one is, as you might have guessed, or maybe guessed, it's how the wings are going up or down. If you look on most modern aircraft, or airliners at least, you notice that the tips of the wings are actually up. That kind of creates a stable equilibrium, so it prevents it from rolling. So that'll look like this. Draw another airplane here. Over exaggerate it right there. I don't think this airplane would fly that well. This right here is called wing dihedral. No, I didn't spell that right. Dihedral. And as you might have also be thinking, if it goes the other way, right here, so it'll look like this right here. Uh-oh. Looks kind of bad airplane right here. Goes like that. That looks almost like a spider. That right there kind of creates an unstable equilibrium, and it kind of wants it to be tipping. You might be asking, why would you ever want to do that? Well, the answer is sometimes if your wings are swept back too much, like this right over here, like this guy, you might create so much stability that it's almost impossible for it to turn, even when you're trying to intentionally turn it. So you might have to add some unstableness. Also for military aircraft, where they have to be able to roll. In an aircraft passenger, or an airliner, you're not going to really want to be doing barrel rolls or turning really sharp. Okay, and then the third one that affects stability is a T-tail. And that looks like this. I'll try to draw a better aircraft. There's a T-tail up here. Okay, that looks a little better. It's this T-tail right there. That also creates some stability.
Okay, here is an example of what I'm talking about for stability and design issues. Here is a picture of the C-17. If you know anything about the C-17, it is a military transport. Means that you drive tanks up into the back, or really heavy cargo. So as a result, you have to have really high wings in order to get the clearance required for this. I guess I forgot to mention it earlier, but in addition to a really high T-tail like you see on the C-17, really high wings also create a high stability. So you have this really high stability caused from the up high wings and the T-tail on the back. You're going to start to be able to have a hard time turning and doing maneuvers intentionally. So it's a really stable aircraft as it is. So in order to counter that, you see how they have the wings pointing downwards. That counteracts some of the stability caused by those two other factors. That's just kind of a quick example of how the design and the intention of the aircraft kind of play a factor into how it's designed. You have to have a combination of these stabilities and unstabilities in order to have a usable aircraft and still complete the function that it was intended for. So that's just a quick example of how that plays out, how you design an aircraft based on its design purpose.
Okay, moving on. Next we have aircraft operations. For example, I won't go into too many specifics of these. We have pilot training. Pilot training, for example, it simulates flight. it directly applies these equations of motion we'll be doing. In fact, modern day simulators are actually so accurate or so realistic that many times you can actually have in some of these newer aircrafts, your pilot might actually be a first-time flyer, first-time pilot of an actual real aircraft. The catch about this is there's two pilots and one of them has to have real-life experience, but you can have a co-pilot who has never flown an aircraft before. So that just gives you an idea of how accurate we have gotten these equations of motion down in the first place. Equations of motion down. Another example, we have accident investigation. This, as you might have heard of before, is called the black box. This black box right here contains all the inputs that the pilot has made into the aircraft, all the conditions about the aircraft for a extended or for a period of time, and common misconception, it's not actually black, it's bright orange. It's easier to find that way. Okay, and then thirdly, we have automation. These automations come in the forms of UAVs. Those are uninhabited aerial vehicles. It's also the autopilot on commercial airline planes. And then fly-by-wire as well. You probably know what the first two are, so I won't go into any details about those, but fly-by-wire is a system, or olden days aircraft used to be directly flown, as it would be a one-to-one motion. The pilot would move his wheel, and then the aircraft would do exactly. They're connected by physical wires. Nowadays, computers are, I'll give you an example. Here's let's just say this is a wing right here, or tail, or some part of the airplane. We have this guy right here to control the elevation. And then we have a wire sticking out here. This wire goes to some box, let's say, that is mounted on some part of the aircraft. So this is the fly-by-wire system. This is controlled by this flight computer. The flight computer is also controlled to, let's say, the pilot control. I'll try to draw accelerator pedal. Kind of looks like one. So when the pilot pushes this, it sends a signal to the flight computer, and then the flight computer will in turn move this. The flight computer also looks at what the pilot says, and it's going to double check to make sure, is what the pilot's telling the plane to do, is that actually able to happen? If not, it won't do that, even though the pilot says do that. It won't do that unless it knows the plane can, because it knows exactly what the plane is limited to from the equations of motion and experimental data. So that's fly-by-wire. That's just this system in place. There's also the other system where there is no flight computer. You can directly tell your plane what to do, and it will do that. Most newer planes run by this model right here. So that's just a little bit about what is FDC. Next we're gonna go over a little bit of vocabulary, because like a lot of different fields of engineering, there's a lot of notation that you just need to know, and it makes things a lot easier if you know what it is.